Hello, my name is Isa Long, and today I'll be explaining my one proportion z-test. So the prompt that I ended up going with when conducting my one proportion z-test and my two proportion z-test was the M&M one. So I ended up getting data values of my own, and I got 15 bags of regular milk chocolate M&Ms, and as a total there were 855 candies in all 15 bags, and out of the 15 bags there were 173 blue out of 855 total. So I ended up using the proportion of 0.24% because that is what's stated in the prompt for my hypothesis. So the null hypothesis would be P equals 0.24, so the regular bags of milk chocolate that I got data values of my own would equal to 24%, just like the statistics stated. Or the alternative hypothesis, which would mean that it is not equal to 0.24%. This could also be represented with like an equal sign and a slash in the middle, but I didn't know how to do that, so I just put not equal to 0.24. So the alpha level would be 0.05, and here are my conditions and my condition check. So for the randomization condition, all bags of M&Ms were randomly selected. There was no pattern, and so this condition was satisfied. As for the independence condition, there's no reason to think that the probability of one bag consisting of blue M&Ms will affect the probability of another bag. So they're unrelated and separate and should have no influence on each other. And 10% condition, it is possible to assume that less than 10% of the M&Ms have been sampled, since there is likely a large amount of M&Ms produced each day that are well over the amount sampled. So as for my success and failure condition, you can see my sample multiplied by the probability, or my sample size, or n, for 0.24 and then 1 minus 0.24, and you can see it's well over 10. So there are at least 10 failures and 10 successes, so this condition has been satisfied as well. And because the conditions are satisfied, we will now use a normal model for the sampling distribution of the proportion and perform a one proportion z-test. Here we're dealing with a two-tailed test, since we have a not equal to for our alternative hypothesis. Here are my mechanics. You can see all values found here, like the p-value, the z-score, the standard deviation, all that's required in order to find the values we need to conclude. So the p-value I ended up getting was 0.005, but since it was a two-tailed test, I would have to multiply that by 2. So the n value, or the n p-value, was 0.01. And so since that is lower than the alpha level, we can already tell with our regular normal model that it is in the rejection zone. So since since our z-score was negative 2.60, right off the bat we can already place it on our regular normal model and see where it falls. So this is the rejection zone right here, and we can see that it falls there. So we would already know to reject the null hypothesis. There's another normal model that I ended up making for the p-value. It's basically the same thing, shows the rejection area for where the p-value stands in the normal model. So this is where we can tell as well. And to conclude, our p-value is less than alpha, which is our alpha level or significance level, which is 0.05. So because of that, we need to reject the null hypothesis, and since the calculated p-value is 0.01, which is smaller than 0.05, so there's sufficient evidence to warrant rejection of the claim. So overall, there's enough evidence to presume that the proportion of blue M&Ms in other M&M bags is different than 24%, or it is not equal to 0.24%, like the statistic stated in 2007. Thank you.